in space engineering at Politecnico di Milano, if I'm pronouncing it correctly, Italy. He is on a break due to this pandemic, and I'm thankful to him for spending this time on a beautiful Sunday for enlightening the juniors who have joined this meeting from various places. I thank the KCG for hosting this webinar. We'll proceed with the webinar. In case if you have any doubts, you can post your message in a chat box. The host, Mr. Shamnarayanan, will enable your mic. In case, you can also use the option of raising your hand, which is available in this tab. Thank you, Anandal. Over to Dinesh.
Okay. Good morning to all. So myself, Dinesh Brindavanam. So I'm here to present you the use of OPENFOAM to CFD. We'll start the lecture.
Yes, Dinesh, you can go.
I hope everyone can see the slides. Okay. Since we have a lot of young engineers in our group, so I'd like to give an introduction to CFD, which will be giving you an idea what is this CFD. So CFD is a computational fluid dynamic. This system of analyzing method is used to solve major heat flow problems, then fluid flow problems, and some kind of chemical reactions. And we use this one based on computer simulations. This tool is preliminarily used for getting to know to solve your PDEs, partial differential equation, and the CFD fundamentally works on the principle of solving these three governing equations. The first one is mass is conserved, then Newton's second law, and energy equation. So what is mass is conserved is like if there is a control volume and some fluid passes from one region to another region, we know it sure that the fluid completely passes from the entire volume. It is some fluid may be stagnated inside the body, as some particle may get evaporated or some other phenomena. But a general CFD simulation involves in finding what is the rate of flow which is going to take place from one end to another end throughout the control volume. That is known as mass is conserved. Newton's second law deals with the forces. If you take a solid block of something where some fluid is flowing through it, we try to find what is the force acting along the surface, internal volume, what is the force. So we need to conserve those forces also. First we conserve the internal mass, next we conserve the forces which is going to act in between. Next, energy. There can be internal source energy. So there can be some form of heat generated or dissipated, or some other form of heat energy being added to the system or removed from the system. So we need to determine what is those energy, whether it is completely balanced. So these are the fundamental principles which the CFD is going to use to solve our problems. Next, the CFD is purely based on numerical methods. It it is used to solve problems related to space and time. So we are not going to solve only in a space region. Like if you have a pipe, we are not going to solve what is going to happen within the pipe alone in a constant time. We are going to move and time what is our solution, numerical description of the problem based on space and time. So what we generally find from CFD. So you may be interested, like for example, if you try to solve some kind of mathematical equation, you should know what you're going to what you're trying to find from that particular set of equations. So basically, in any fluid flow problem, the basic fundamental unknowns are your velocity, your pressure, and your temperature. So these phenomena need to be we need to find it from our CFD solution. So how we are going to find? So basically we have 7 unknowns basically. So what are those unknowns are? We have three velocity components, then you have pressure, temperature, then you have your density. Apart from this, there can be turbulence models which you need to include in your solution, but for the simplicity, I'm not going to include this thing. So we have 6 equations to be solved. So this 6 equation, how we are going to solve it is using 6 unknowns. 6 equations. Those equations are 1 continuity, 3 momentum, so it becomes 4. Then you have energy equation. Then you have a any ideal gas equation. It can be an ideal gas equation, or you can use some other equations to find the density parameters for the flow. So we get a well imposed equation to solve our problem. So we have 6 unknowns, 6 equation to solve those, to determine those unknowns. So now we need to solve it in numerical methods only. So we are using a method like only a computer can know to add, subtract, multiply, and divide, and it can do only simple logical operation, and it displays colors on the screen. So how we are going to use the advantage of the computer, what capacity a computer has, how we are going to use those things to determine the solution of our problems. So first one is analytical solution, and another next stage is numerical solution. So why we need to use CFD specifically to solve any problem? You can use even hand calculation, all those things. So why we need specially CFD? CFD is now the fundamental tool used to solve unsolved engineering problems because of the complexity it adds to the problem. The need for quick solution. We need obviously quick solution. We cannot wait for years to find a solution for some problems, which is will cost you both time and money. Next is some problems it can have, you cannot find some analytical solution to it, because some problems may involve in some recirculation flows. Generally, recirculation flow problems cannot be solved directly by hand calculation. So we need to use some other methods to solve those things, and CFD plays a major role to solve those things. Next, it is we need to develop an efficient algorithms to solve these things. So you need to be fundamentally trying to understand how a computer works, how mathematics you need to implement, and how physics works. So if you are able to mix all these 3 ingredients properly, you will be able to get a good estimated values of the unknowns, which I told previously. Those are pressure, temperature, and velocity. So since a computer we are using, we need to know like a computer is not a single machine. It is like a labor of multiple labors working together rigorously to get some output. So you need to know how to use this labor efficiently, not like a single labor working and other labor ideal. It's not like that. We need to make whatever you're trying to solve, you need to distribute those work equally towards all the workloads of your labor. Like way you need to parallelize the computing. Then you can, once you've done this simulation, you can get whatever values whenever you want after the simulation. So it's not restricted to find those results only at that particular specific time. You can do it whenever you want. So once you get your simulation, once you get the output of the solution, you can determine the values and the unknowns or some other derivatives of the unknowns also whenever you need. So what are the general procedure which we are going to do in CFD process? So this is a very generic phase. I hope everyone would be able to get a glimpse of what is going to happen in the upcoming slides. So first we need to create a virtual model. So what is a virtual model is a CAD model. Generally a computer cannot model cannot understand the geometry just by hand drawings or those stuff. So we need to create a CAD model to the geometry. This CAD model is built on any platform. It can be in SolidWorks, Pro E, or CATIA. It can be in any part of the CAD modeling domain you can choose. There is no restriction. But once you have generated this CAD model, you need to bring it to the CFD solver using a particular standard formats only. There can be a native format and a neutral format. So what is a native format is, for example, if you take CATIA model, so once you're done your CAD modeling, you will find that the CAD model gives you some output which is in the file format of .cat part. So this specifies that this model is again editable in the environment of CATIA. So the CFD solver cannot use this kinds of model. It can only handle something like, it should use only a neutral file format. Like for example, these are some file format which I'm specifying it to you. It is a .igs, .stp, .stl. These are some of the neutral file format which you can use to bring your model which a CFD solver can understand. Then we need to go on with discretizing the domain. What is this discretization? So generally, I told you you're going to solve some set of equations first. So how you're going to solve this set of equations? Basically, you need to use some methods to solve these kinds of differential equation. So what is differential equation generally? What is generally differential is, you are trying to find what is happening in the smallest domain possible. So what we are trying to do is, we have a set of equations, okay, the governing equation. This governing equation need to be brought into the platform of smaller level cells equation. So what you're going to do, this set of equation, we are going to bring it to the smaller domain. This smaller domain is called meshing. So meshing is a way of building this entire domain. I'm not going much about the internal part of this equations and mesh all those information. Why? Because my ultimate goal, what I want to give you is towards the OPENFOAM, the fundamental tool which you will be using to solve those problems. So I'm not going depth of it, but you can, in online searches, you can get a lot of information regarding this, these things, like what is a mesh, because it's like a heart of the problem. If your mesh is not proper, then your results won't be as accurate as your real world outputs. So you need to be very careful in handling those things. Next. So once this equation, we need to bring it to from that general equation to a smaller level. You're going to distribute this equation, solve this equation in individual domains. Whatever you split up, the geometry is there, you want to split the geometry. Next, you want to go to the numerical solution. You want to find the numerical solution of the dependent variable at the discrete location. What is discrete? It is like there is some finite distributed nodes and elements, which are like the key terms which you use to describe a mesh. So there are like points are there. It is connected by a line that is known as elements. A node is there and element is there, which are connected together. There's a chain of cells which is connected all together throughout this entire your model, whatever desired model you are using. And you can, through this, you can find what is a chemical reaction of a flow and a multi-phase problem, mixing phase, mechanical movements. You can do multiple things, but you should be careful in doing this, because the output, whatever it comes from the CFD, is not 100% accurate until it is properly set. So you need to know how to set a problem. So it comes by a huge time process, where you do start doing a lot of process, a lot of simulation, and then you get some output. You compare those things with an experimental and you get to know. Okay, so now I'm giving you a glimpse of what are the different methods which is currently adopted by multiple peoples all around the world, and why CFD is going to play a major role for the upcoming years, and what it has done good in the past years. Now how it is going to expect to be very good in the upcoming years also. So generally there are three methods which everyone follows. One is the experimental one, analytical one, and numerical methods. So what is an experiment? You would all be obviously know that it is setting up the problem in an laboratory condition, and you're trying to get some results. So it is has a most realistic approach. It has its advantage, but the disadvantage is you need an equipment, and there can be a scaling problem. For example, you're trying to analyze flow through a pipelines, like you want to find how much pressure is dropping across a very huge long pipelines. So in that case, we cannot get those pipelines for those many kilometer lengths to simulate it. It's very much costly. So what you cannot do, the scaling problem also occurs. There can be a measurement difficulty and probe error, like an instrument used to measure those readings, and it can be high cost operation. For running an individual experiment, you need to spend a lot of money. Next is analytical method. Usually this is generally using the formula which you observe. Generally this is a way you use to solve your problem. Whatever you're doing in your engineering life, in your bachelor's, is generally you try to solve these things in an analytical approach. So you use some equation directly to find what is a pressure drop across the end of a pipe, or what is the pressure distribution across your airfoil and all those things. So use an analytical method, generally using a formula. This is restricted to simple geometry only and physics. So you cannot use this one for a very complicated geometries and complicated physics, like finding what is a conjugated heat transfer between two airfoils, or high temperature flows, all those things here. So it is very difficult to handle, and it is restricted to a linear problem. And the results could be you can get the results, but it is difficult to compute. So you need to spend enormous time in computing the problem. So if you slightly change the geometry, then again you need to recalculate the entire thing, through which your solution is going to be you need to spend a lot of time to get those solution. Next is numerical methods. This is it doesn't have any restriction to linearity. So it's not necessary a geometry should be properly uniform, no irregularity in the geometry, and it can cost you very low, and it can do high computation. Whereas the disadvantage of this one is there is a three major error which you need to understand once you get into CFD. So once you do some CFD analysis, you get some results. So how you will evaluate these results are better. So first you need to know what is that truncation. So I told you it is going to be a numerical method. So it is going to be adding two numbers, or subtracting, or dividing, or multiplication. So while doing this operation, there can be a possibility that a pressure value, for example, I'll tell you, a pressure value can have a reading of some 5 into 10 power, some 10 power 6 pascals. So what happens is, after 5, there are some 6 digits which is going to be present inside the number. So what does this truncation error is? So you need to store this 6 digits into your computer memory. So what is going to happen? It is not an easy task directly to store those numbers. So the computer has a memory restriction also. So what it does is, it cannot sometimes it cannot store 6 digits. It chops off the last 3 digits, and it considers only first 3 digits. So what happens is, it truncates the numbers. It doesn't go directly. The next one is round off error. Sometimes what happens is, those during this cutting off of these numbers, these values are rounded off. Like if it's above 5, it adds one number to the next digit. So a general rounding off is made to this one. So what happens is, over the series of time, you get the numbers chopped off regularly and rounding off regularly, so that this number error keeps on adding to the problem. Next, the boundary condition problem. The boundary condition problem is really uncontrollable problem. Why? Because you're trying to depict some flow through some channel or something. So what happens is, once you try to cover the face of the problem, like the inlet, for example. So inlet, you try to give some velocity component. Okay, consider the velocity is around 10 meters per second. So you can see this is the exact 10 meters per second, but actually this is not the exact thing which is going to happen in your pipe. So what happens is, there is a curvature. Like, so the center one may experience 10 meters per second flow, whereas this way may experience some 8.2 or 8.3 meters per second, because of the boundary layer problem. So this one, what happens is, so you're in the initial problem itself, you're not trying to get the exact boundary condition to the problem. This can be avoided by taking if there is a pipe which you want to simulate for 10 meters, you try to take a pipe of 11 or 12 meters, 1 meter extra, and try to give those inlet condition well ahead of the boundary, well ahead of the desired geometry. so that the fluid flow nature will develop internally, and you will get your better result at the exact place where you want to start. This can be one of the way to solve the problem, and there are multiple ways also. Even you can give the boundary condition as a type of the boundary, the type of the flow which you want to give up. Next. So next is the we need to know why CFD is the best approach compared to all the three, due to its less cost and high reliability. CFD is as an equal partner with pure theory and pure experimental. It is synchronistically complement. So if you should be really fundamentally strong in theory and fundamentally strong in experiment to get the work done. So you need to spend a rigorous time in learning the theory of the problem and the experimental setup of the problem. So once you get it, once you get some output from the CFD, we can well validate it through the experimental results. So you need to know the in and around what is going to happen for that particular field of domain. So once you join any organization or anything, you may not be doing a CFD analysis one day with some a flow through channel and one day with some spacecraft. So you will be attached to one particular domain for a very long period. So you need to keep on learning how in and out the problem is and how it grows over the time. Next, it is very effective in parallelly doing the approach. Parallelly, you can do multiple simulation rather than waiting for an experimenter to be set up with single thing. So these are some advantages of CFD. One is it is an alternative cost effective measure. That is the main goal of using CFD, because 2-3 decades back, we didn't have a powerful computer to solve those problems. So at that time, the CFD was not much matured to be implemented on computational level. But now it is very much matured, and we are able to do some brilliant work using CFD. So it gives you a better insight and foresighting of the problem, and it is efficient. If you are designing something for a long phase, as an example, if you are trying to design something, some aircraft model or something, so you cannot simply model each and everything for every day and then you want to test it. All those things are cost effective, but a computational model is not going to cost you much, because it is pure easy operations which you are going to do using your computers to get your CAD model done. And using that, you need to implement CFD to solve and get your outputs to find what is a better design parameter which you can significantly improve over the time. Okay, so this is places which you will be using it in engineering testing. It reduces the engineering testing cost, and it reduces the product to market time. So once you are into the domain of an organization, you want to spend a little time in getting the products to be developed within a short time and get it to be marketed, and you need to realize the model and start building the model and selling to the customer, or even you can develop some R&D works also. Okay, so these are the fundamentally the industries which you will be seeing in future, or related fields who will be working towards application of CFD. It can be aerospace. There are a lot of works and aerospace industry does a chemical, mechanical, biomedical, aeronautics, then architecture, and many more. You can see some of the pictures. I don't want to add so many pictures because I want to make this presentation a lot more interesting by a new approach to CFD. Okay, so this was the general part I have submitted. So we have some questions. We have Sanjeev, who is asking, like, is that each element of the mesh is carrying all the 6 covering equation, getting the value of by the partial differential through matrix? Yes, absolutely, Sanjeev. The mesh, whatever you're doing, the 6 equation needs to be solved in the individual mesh cells. It is not over the global cell. So it is solved in the locally, the individual mesh only. So I think you get the answer. Okay, next. So this is the interesting part which I want to share you, because most probably I would like to encourage each and every students to get to know about open source world. So I'll give a brief idea of what is open source. So generally, whatever software you're seeing, for example, mostly once you search CFD, you're going to see one thing called ANSYS only. Majorly, it is going to be ANSYS only. ANSYS, then CFX, star CCM, all those things. See, these are very good software, but these are the black box. I would suggest you not to, maybe in your bachelor's you may be using it, but don't try something which is purely black box, because during my bachelor's, I spent a lot of time in using these commercial tools. Later, I realized that I can be specialist in using all those tools. But the real problem is if someone tells me in those times to solve some problem, basically, it is very difficult for me to solve it on a computer without any software. So the Answers and all are the very good software, but it is suitable for rushing companies who wants to rush their work to be completed in a shorter period. They don't want to spend time. But with that knowledge, you cannot get to know all the real depth of the beauty of any commercial software. Okay, so here I have added some of the commercials. These are some open source tools which are available to you. I'll show you some more in details where you can find these tools and how to learn these tools. So many people would have not even heard about these tools, because these are fundamentally developed by very small group of people, and it is purely restricted to certain applications only. But whereas OpenFOAM is well matured in our field, which you can utilize for multiple purpose. Okay, and there can be multiple softwares, and this is one of the another famous software which is becoming very much useful in the application of CFD. This is called Stanford University 2. This is a code which is developed by Stanford University students to solve some CFD problems. So basically, you need to get to know these kinds of softwares. These are the software where you don't see any kind of window or GUI or anything. So yeah, there is another question on how many mesh size you can use to solve the CFD. Okay, there are some slides which I'm going to come through, but to give an idea, there is no limitation on number of core number of mesh you want to use in OpenFOAM. There is no limitation at all to use this software. You can use whatever you want and whatever capacity you want. Only problem will be your computational resource, that is your computer hardware, how much it can handle. Apart from that, there is no limitation at all to use how much ever resource you want to use. You can use like 1,000 core, one core, or even like million cores of processor to do the problem. As well as you can use how much ever mesh size you want, you can use. There is no limitation at all. No one is going to question you on how much you are limited to use. Okay, so this is now I'll try to go briefly on one tool that is called OpenFOAM, which will be the hot topic of our discussion today. So OpenFOAM stands for Open Field Operation and Manipulation, and it is developed based on C++ language. So first, one thing I'll tell you is once you graduate from your bachelor's, once you start seeking some job and all, it will be very difficult for you to get job in the field of CFD, especially if you want to be if you want to be attached to some R&D sector. It is not at all easy to be attached to some R&D sector without knowing the knowledge of programming. So better spend some time in learning some program. You will never regret in your life when you spend some time in learning some programming. So better sit and learn some programming language. Here I'm not going to stress you on which programming language to learn. You can learn any programming language. It is like a tool to solve your problem. So it can be Python, C++, C, or Fortran or anything. So it doesn't have any restriction on what you need to use. So, but this OpenFOAM is fundamentally built on C++ platform, where you're going to use to solve some partial differential equation and some ordinary differential equation. And it comes with ready to use. So you don't need, once you install the tool, you don't need to customize the tool or something. It is pre-built and it is well developed so that you can use directly. And it is licensed under GNU. So what is this GNU is? See, once you come and start working with the open source organization, open source tools and all, this will be licensed under GNU only. These are the open source forum where the developers from different world are come together to develop softwares when they are at free time or they do it at full time. You can also do it. I'll tell you how you can join those community and start working on your own, so that if you don't get immediately job also once you graduate, you can work on something real projects with at no cost. Just you need to get connected to the system, and you need to spend a lot of time rigorously trying to understand what architecture they have came across to build this platform, that particular tool. Then you can learn those things basic and then start contributing to that one, so that then upcoming years your contribution can be part of that original source code also. So I'll tell you how it comes with something called GitHub. And it can be massively parallel on a parallel computing. So there's no restriction like what you want to do, all those things. It can be, you can do it on anything for a very long period, and it is under active development. And this means like it is keep on it is kept into testing and development over a long period, and it will be still doing it, and it has been supported by a wide community of people. So it is not like some companies like private companies and commercial softwares like Ansys or Siemens or those companies, where those companies hire some people, they pay some wages to them and get the work done to develop their software, and this software they sell to the people like the users like us or some organization, and they gain that money, they give again that money to the people who's working in the company as a salary, and those people again will be working and getting. So this is a chain process which happens, whereas this open source world is completely interesting and new, will be new for you. So what happens is, so once you are in free time, you contribute something. It is just like the world is going to contribute upon something, so there is no restriction. You can use someone's tools also for freely, and someone can use your tool also freely. So here everything becomes free to use. So because of this, there is no privacy issues, all those things. So there won't be pirating of the software, all those things not going to happen. It is going to be much clean and easy. So you can spend some enormous time in dealing with using the software for free of cost. So you are not going to pay anything. So that is the hardcore advantage of using this kinds of tool, which I want to share with you. So what this OpenFOAM is capable of, you may think like, okay, it is free, so it may not have enough capacity to solve some real problems. No, not like that. It has a lot of capacity to solve any kinds of fluid flow problem. It can solve heat transfer problems. It can solve combustion, chemical reaction, multi-phase problem, mass transfer, particle methods, then stress analysis. It is not only limited to CFD. That is also an interesting part to it. But it's not well matured in the field of structural analysis. So, but still it can handle some basic problem, and it can solve some rotating initial phase problems. Like if you are analyzing a turbo machinery components, you need to start rotating the turbo machinery to find what is the pressure distribution, velocity distribution across these blades, all those things, and dynamic mesh modeling, 6 degree of freedom problems. Like there can be like an interesting topic which I'd like to share you at this point is, when I was working with DRDL, there was a problem which we need to solve to find the motion of the missile dropped at dropped down over a distance using some 6 degree of solvers. So what it does is, once an aircraft is there, so once you want to simulate how this missile is going to behave once it is being ejected from the aircraft. So we need to study how this one is going to take place, how this missile, because we need to give some criteria to the pilot, how to at what pitching angle we should make this missile to be dropped. For example, you're going at a very high speed like Mach 2 or something. So during that stage, if you are dropping the missile and it is you are trying to pitch up the aircraft also, there is a more probability that it can, once it is dropped due to wind pressure, it can again hit you back and destroy aircraft. So you need to design these things and all. So this is basically we try to solve using 6-degree solvers, which is a pre-built on OpenFOAM and aeroacoustics, and you can even solve computational electromagnetic and those things. So why we need to use this one for as a replacement for this commercial CFD tool? This is a important thing which you need to really understand before utilizing the tool. So it doesn't have a native GUI, first of all. So there is no GUI, and also you'd be, once you have used these kinds of commercial software, you'll be surprised to see there is nothing GUI, but how to handle it. These are like command line interface. So it is like just command line prompts, which we'll be seeing in the upcoming demo. And these are built on Linux system. So once you start using this open source software, you need to be well versed in using this Linux platform. Linux is again an open source platform, so you don't need to pay anything to get the version of operating system you want. So it is completely different platform than Windows. So all the engineering students must give, at least spend during their bachelor 6 months trying to uninstall Windows and sitting with Linux system. Even you don't know to use, you better struggle hard to learn it. You never regret in your life that you have learned Linux. But once you use Windows, it becomes much comfortable, because those are private company which wants to sell those software. Whereas Linux is not like that. You need to spend at least 6 months to get to know these things. But it is well worth spending those time, because you are spending 4 years to study engineering. Later you go for your masters, all those things. During that stage, you are seeing almost 6 years spending to learn something. It is not a difficult task for you to spend within those 6 years, to spend almost like six months to sit with Linux. So try spending time to learn Linux. Okay. There was some question on 6-degree solvers. So I think I answered it before. It is based on to find the 6 degree of motions, like to determine 3 positions and 3 velocities. That's all. It is like in 3D space, if you want to find the position of the object and its corresponding velocity at that particular instant of time. So this 6-degree solver is used to solve it. Okay, I hope Sanjeev gets the answer. Next, the only problem with this thing is it's not well documented, because I told you the contributors are like doing it in their free time, and they don't get paid much. So not paid much also, it is like zero pay actually, but the code is developed. So in this way, there is no proper documentation on how to do. That is the only drawback of this open source, but it can be overcome by your own creative approach to keep on using the tool in a random way to find it out. And there can be a lot of resources available at the current moment, so it will be easy for you to handle, and your source code is available to you. So whatever you want to customize, you can do it. But with commercial software, you can never touch the internal code. It's completely blocked. You cannot touch and do what is happening inside. You cannot change it to your desire. Nothing you can do. Only the developers of the company can do it and give it to you at your purchase. Next, it is not a black magic, so you don't need to be worried about how the things are going to be happening just by seeing from outside. You can spend a lot of time in knowing what things are happening. So once you are doing a CFD process, you can know how to change the code, tweak it, and get some results better than the regular one, like knowing how it happens. And one more question on about the errors. I don't know when I got the question. I will reply to you. There is some question. Okay. And the solver can be tailed to your way. So it is no restriction on how you're going to utilize the tool. You can tailor it on however you want. Like you want to solve a problem at a very efficient way, or you want to do it at accurate way. So it can be tailored according to your needs. It is not necessary the whatever the company gives to you, you need to utilize those restrictions, those limitations with those limitations. It is not like that. You can utilize to any other way, whichever way you want it, and it is free. The hardcore, which is going to, as a students, which is going to support you, it is going to be free. So you don't need to be worried about those license, all those things. Then it has no limitations on number of cores you use. So basically, you don't need to be worried on number of cores which you are going to utilize to solve this problem. Okay, now I will show you how to install OpenFOAM basically. So in this slide, I have attached two links which you can utilize to solve it. Basically, these open source tools are very highly efficient on using on Linux platform, but I hope mostly many of them have not learned to install directly on the Linux platform. So I have attached a Windows platform, which today I'll be showing also. So it will be easy for you to give a try first to learn the basics. Then you spend some time installing Linux and using this one and trying to implement some CFD problems and getting some results. So I'll show you how to do it on Windows system. So the link is here. So I'll try to. Okay. So this is the page. So these are the. So these are the this is a software which is developed by one company called CFD Support. So what they do is there's a place where they get this software and they build it on the Linux Windows platform. So you just give download OpenFOAM for Windows. You give some basic details of yours and you accept it and download. You will get some package and you try to install. There is some sequential things parallelly which you need to install. There is some 5-6 things which will be, it's a single package. You need to install it parallelly so that you can get like the entire package installed on your system. This is on the Windows platform. For Linux platform also I'll guide you. So this is the Linux platform. Okay, so this is the Linux platform. Linux is a pretty vast operating system, so you need to choose the corresponding version of Linux which you are using. Basically, everyone will be easy to use Ubuntu version. If you go to Ubuntu, just you need to follow these commands. That's all. You try to install it basically using you just read it, and it is very much easy. Just some process of installing up to this one. It is very easy. Just you need to copy paste this one and paste it on a terminal, which once you install Linux you'll be getting to know, and you can do it and entering this command and getting your results. This is like a fundamental way to install it. So this gives you an idea on how to install OpenFOAM. Now we'll see how an OpenFOAM looks like. So for example, you may be visualizing this one. This is the basic momentum equation. Okay, so I hope this equation is a pretty much reduced form, because another one important thing about open source tools also. See, this open source tool is not developed by Indians or some Russians or some people in US. It is being done by group of people who are there all over the world. Even I can contribute, you can contribute, anyone can contribute to it. So in this scenario, how things happens is they need to bring it to a common platform. So all this symbols and signs which is used here are pure. If you see some international author books, you can find only they use these kinds of standard the divergence and the Laplace transform, all those things. So this entirely is based on the international standard of representation of the mathematical equation. So try to get familiarized with these kinds of mathematical equation rather than simple equations which you observe from the Indian local author book, especially because you will be studying those things for your exams, but spend some time in reading some foreign author books where you get familiarized with these kinds of equation. So this simple equation, now you see how it is written in OpenFOAM platform. So this is basically written on the C++ language. So this equation is built on like this. So I'll give you a glimpse of it. This is a finite volume method, which is going to be applied over the differentiation with respect to time into rho into u, which is this part, then plus the finite volume method of the divergence over phi and u. Okay, and minus the finite volume method of Laplacian. This is a Laplacian operator over mu into u, then equal to minus finite volume calculus of gradient of p. So this equation will be written in this form. So once I show you the solver, all those details, you will be seeing like this kinds of things only. Next, this is the OPENFOAM toolbox has the inbuilt solver. So once you use OPENFOAM, you will be seeing these kinds of solvers. Okay, basically when I started learning OPENFOAM, the problem was I was unable to find which one to use for which one. Okay, because there is no proper documentation. So it takes you a lot of time. It takes you around 1 or 2 years to really nail the problem of any CFD problem using OPENFOAM. It is not like 1 day process or 2 day process or 1 week also. It takes time. But the time you spend to learn OPENFOAM is really it is like you spend time so that you don't spend any money later in your future to solve some problem. Basically that is the key point which I'm trying to highlight. So once you learn OPENFOAM, spending a lot of time, you will never regret like later like why we learned it and now we are spending a lot of money to solve problems. No, it is not like that. But once you use commercial software, you're going to regret in the future stage, because software may be updated to the next version. They'll tell you to pay some lakhs of rupees, because commercial tools are not cheap. They are very costly. For example, ANSYS can cost you around 45 lakhs for a full capable license of an individual user also. And if you're going like a group organization license, it can go up to 2 crore to 3 crore or to 5 crore also, depending upon number of course. So you need to buy the license for number of CPUs you are using also. So it is like number of CPU as well as number of license. So it is like a multiple numbers which will drastically increase the cost of the commercial tools. So as a replacement, we are trying to use this tool to solve those problems. So you'll be getting the slides in the end of the session, so you can spend time what is this solver solve, which to choose and all. Basically I'm telling you glimpse like if you are trying to solve some incompressible flows and all, you need to use icofoam and simple foam. If it is a compressible flow, row simple foam, sonic foam, and combustion, DNS model and LES model. This you need to spend time in learning CFD also, because I have not touched anything on depth of CFD also. I'm giving the overall picture how to use this tool to solve those CFD problems. And I told you before, we need to get the mesh done. So mesh, you need to understand it is a different approach in OPENFOAM. It is not like some tools which you use it in commercial softwares to generate mesh. In this one, you use something called block mesh. These are the mesh tools which are integrated with OPENFOAM. The first one is block mesh, in which you need to create a coordinates for the block which is going to be attached to your geometry to get the mesh. Okay, these are once I show you some fundamental problems, you can understand there is some file called block mesh. Okay, there is something called snappy. This is very powerful tool. So you need to spend rigorous time to know how to use this tool, because these are if I tell tools, it doesn't mean it has some GUI and all. It is a text-based file. It is like a text-based file of some 100 lines, 200 lines. That's all. So you need to know how to tweak these text files to get your work done. And there are some other meshing tools also. So if you ask me like, okay sir, like whether using only the inbuilt mesh tool is the only option to solve the CFD problem, means I'll tell you it is no. So you can use any meshing tools. It is not only the meshing tool which is available to you through the CFD. You can use any meshing tools, basically ANSYS Fluent or something. So once you have done those meshing, we need to convert those meshing using these kinds of command line prompt. So you can solve it. I'll show you an example also how to use this one to solve your problem. So you can even generate your mesh using Gambit, and again you can convert it back to the file which OpenFOAM can understand to solve the CFD problem. So these are some command line which you can spend time in realizing what are those things once you start installing this one. So there is some helplines also which is available to you. So there is no restriction on how to restriction on how limited the software is. It's not like that. You need to explore yourself, spend time in understanding these things. There are a lot of helpful resources which I would have attached here and there to get to know about these things. Next is the file system. So what is this file system is you need to solve some problem. Okay, so we need to understand how this process is going to be carried out. Basically the entire process is going to be done within 3 files only. Okay, there is going to be 3 folders which you will be seeing regularly. Okay, one is called 0 file, another is this time directory is called 0 file, then there is a constant file, then there is a case file. So what are these things? These are the internal files within those things only. These are the entire thing which you need to solve any CFD problem. Okay, based on the complexity of problem, this internal file script length would be longer, that's all. But fundamentally these are the things which is going to be inside. I'll show you detail also what are these things. So I told you there are going to be 3 files to it. So one is a constant file. In constant file will have scripts of only the files which is not going to be altered during the entire simulation. Which, for example, mesh is not going to be altered throughout the entire simulation. So mesh is going to be fixed. So your mesh is going to be stored in the constant file. Then some transport properties. So basically these transport properties are like some kinematics which you will be including to your problem, which will be a part of being constant throughout the entire simulation. Next, it is a system directory. So what is a system directory? It is a procedure to set your problems, like how you want to solve the problem. Basically you want to solve it over 10 seconds, or you want to solve it over 100 seconds, or you want to solve it using particular mathematical. So what other schemes are there? What are the other things which you will be knowing? Next is time directory. So in this one, you are going to set what are the initial condition to the problem, because the numerical methods what we are using CFD are initial value problems, initial and boundary value problems. So what are these? What does this mean is, so you need to have some initial value to your problem. It can be any value. It is not limited to pressure, means it should be 0 only, or it should be 100 Pascal only. But the better you give the initial condition, almost accurate to your predicted value, because you may be knowing inside a pipe of 10 meters per second flow, you cannot expect a flow of 1,000 meters per second. Obviously it cannot be. So you cannot initialize the a problem with something of very high numbers. So you need to give it approximately the value which will be regularly found within those regions. So obviously 10 meters per second would be a better guess compared to a 1 meters per second guess or a 100 meter per second guess, because we know maximum flow region will be that much only. And we need to give the boundary condition. What is going to be our boundary condition? Okay. Next, so I told you these are the basic 3 folders which you will be seeing in your which will be used to set your problem. Inside the constant directory you will find polymesh, where your mesh information are there. I'll show you what are these mesh information also. Some transport property like viscosity, all those parameters, which is going to be constant, which is not going to be altered at any cost during the problem solving. And these are some header files. Okay, so once you open these scripts, you will find some header files to the problem, to the scripts. So there is some header file where it gives you the there is something called like this, you will be seeing. Okay, this part is actually this one. What does it mean? So once I see this one, what I see some dimension 0, 2, -1, 0, 0, 0. So what does it means is this one only. So it tells you the SI unit of the SI unit of the physics. So it is kg. General SI units are in this form: kg, meter, second, Kelvin, then mole, then ampere, then candle. So these are the units of SI units. So this one directly corresponds. So what I mean is, so dimension 2, so means meter square per second. So what does it specify? It specify the specific density. Okay, so you need to use this one to know this one. So once you're stuck with some script, you don't know what is this script is for, so you can basically find the dimension of that one, you convert it, you can find what is the unit, what is the property which you are trying to find from that particular script. Similarly, this is on system directory, the second directory file, in which you will find the internally there are some files which you will be seeing. One is CONTROLDICT, then FV scheme, FV solution, then decompose part bit. I think these things will be very new to you. So, and as well as I'm rushing also, you spend some time, you can get to know, because I have given a description of all those things, but I'll show you a demo also, what is these things also. But don't get panic about seeing what is these new things and all. It is once you get practice, it will be easy. So CONTROLDICT gives you the control. So how much time you want to run, on what parameters you want to set, how much times you want to write the output of the solution, all those things. Then you find finite volume schemes. So what's discretization schemes you want to use? How, like I told you, like you want to use some differential equation to be solved in some particular mesh region. So how you're going to discretize those equation to that particular small domains. A governing equation is there, how you're going to bring it to that small one, what scheme you are going to use, and how the solution type is, what is going to be, what kind of solver you're going to use, all those things. Next is decompose part. So I told you one thing was these things are built on free source, and you have a lot of process which you can be used to run the simulation basically. So what happens is you can run it in parallel on multiple computers. So how you're going to split your domain, that is your mesh, into those many parts. Okay, so I'll show you a demo of this also, how to split your geometry into multiple domains and then get back your results also. Okay, inside solve CONTROLDICT, you find this kind of script. This I'll skip this one for a while because I'll be showing you a live demo also what this is. So these are some schemes which I've attached to the slide so that later you can spend time in learning. You don't need to remember all this lines of code and all. That is one good thing about this kind of open form. So you don't need to remember, okay, this application, this is icoform, this is start from, this is start. You don't need to remember. These are already available to you. Just you need to modify, what is this one? I don't want this one. I don't want to use this one. I want to use a start time of different. So you want to modify only this one. You don't need to even remember. Okay, the toughest part is for example, you are using write control. For example, write control, there is there is some option defaultly set as time step. Okay, what is the other option? That is the difficulty you will be facing. So that one, what you need to do is you need to study the literature and documentation of OpenFOAM, which is very limited, but still if you spend some time you can learn it. Okay, apart from that, you don't need to remember all this equation. And one more important thing about this Linux based systems are, these are basically built on Linux based system. Okay, so it's a case sensitive. So if for example this end time is there, okay, so if I want to write this one, I need to specifically write END as small letter, T as capital, and IME as small only. You cannot put a capital E at the starting and write this one. It is not going to accept. It is going to show error. It is highly case sensitive. So you should spend time in understanding how you are going to do it. Generally, I'll tell you how the Linux developers think. So how Linux developer thinks is, whenever you write something, the starting letter will be a small one. Generally, you see stop at, okay, maybe okay, I'll show you this one because it has 3 words. So So 3 words. So what you see is run is small, then the next alphabet will be, the next word alphabet will be in capital, then the next alphabet will be capital. So you can see it is very much easy for us to read. So generally this is how it is entirely designed. This is not only for OpenFOAM or some other open source software, but in entire Linux based system will be using this kind of ideology only. Next, we use FE schemes. Okay, I'm not going to touch these things also because I'll show you a demo. I'll show you the scripts. You don't need to remember these scripts, so don't worry about trying to remember these kind of huge scripts and all. Don't need to. Just you need to modify it and get to know. Okay, there is a question on what is the basic platform to become a developer in CFD. Okay, the basic platform, I'll tell you about this one. You ask me at the end of the session, so that I have one special keynote on telling you where you can spend time to become developers of these softwares. And so Sanjeev, you ask me if I forgot also, you ask me at the end of this session. Okay, and there is these are the finite volume schemes which you are going to use. Okay, I'm not going to touch the in depth of these things also, but I'll show you a demo of this one. So I'm attached this one to the slide because you will be getting to know these things in the later stages. How to, for reference also, you can check these things. Okay, and this is this is a tool which you're going to split your domain, because you're going to do it running on parallel system, because that is the main purpose which we are trying to do using OpenFOAM, because it is cost effective and you want to solve it in entire parallel domains. And inside time directory, I told you there is a file called zero, constant, and a system file. So this is a zero file. What does it inside has is, it has the header file, dimension, then internal field and boundary condition. Okay, so what are the boundary conditions? Okay, if you have used some commercial software, you would be familiar with these terms. May not be patch, would have been well familiar with wall, symmetric condition, all those things. These are basically the limitation which we are applying to the geometry size, and what nature these geometries, faces or surfaces are going to exhibit during the simulation. For example, if a pipe is there, the external surface obviously is going to act as a wall, so that no flow goes inside and outside. Okay, for example, another example could be an AC ventilation. AC ventilation, where you need to have a temperature difference between the two walls, which we need to compute. So the wall is not going to become an adiabatic condition where there's where it's not going to be adiabatic condition, where heat exchanges are going to happen across this particular wall. So at that time you need to use a different wall condition. Okay, so these are some basic terms which you will be using in the field of OpenFOAM. Okay, these are the script file what you'll be seeing to use it in OpenFOAM. Again, I'm telling, don't need to remember these things, just you need to modify these values only and you will be ready to start the simulation. And this is the pressure one. Okay, and these are some script which I have added to this one, and I'll tell you, like these are for Linux platform. Okay, so there's some tweaking in the Windows version, which you can go to the CFD support, the website which I showed you for downloading. In that itself there is a documentation. For example, if you are using a Linux based system and running it remains the same, MPI run, for running a multi-parallel simulation. Whereas if you are running in on Windows, it is called MPI execute. Okay, so it is slightly different between the Linux version and Windows version. Linux version you will get a lot of documentation, but Windows version it won't be there. But still, I want to motivate you to use OpenFOAM, so I am trying to bring it through Windows version. But if you have any doubts with Windows version, the documentation is available on CFD support, which is the page where you will be downloading that particular Windows version software. And next is reconstruction part. These are like the command line which you will be using to solve in parallel. Okay, and this is parallel simulations ideology. Okay, now I would like to show you a demo. I think it is late, but I think we will try spend some time. Okay, so I'm going to show you how to do some basic example. Okay, first what I'll do is, So once you install this software, that a package I told you, once you try to, don't skip anything, try to install the entire package. It'll ask you for multiple installation. You install all the supporting files also together. So it is around 400 to 500 MB file. Okay. So once you install, it will be default installed on a C drive. Okay. There will be some folder called OPENFOAM. Try to open it, the particular version. Okay. So how it is built is, see, again, these things are again not built directly on Windows. Okay, it is built on Linux based systems only. So what this developer has done is, he's trying to bring a small software which supports Linux, on which the software, this OpenFOAM is installed inside that particular file. So this is the general architecture you will see, like how you see my computer and all. If you go inside your C drive, if you go, you see program file, all those things, same like that. This is the basic architecture for a Linux based system. So in this, if you go, you need to click sysbin. In this, you go to opt. This is a general file system you will see on Linux based systems. Okay, not on Windows based system. Linux based system, this is how the system files will look once you go to the C drive of the Linux file. Linux operating system. In that, you need to go to opt. This is a folder like program files, which is similar which is in Windows. So if you go to in this one, you observe this opt, which is the program file. So you'll find OpenFOAM. This is the OpenFOAM which we have installed. Inside that, you need to go to developer, and you will find applications. Okay, so these are the entire files which is available to you. So I'll show you first how you can access the source code of the thing. So you can go to the application, solvers. Basically, this is the solver. So there is no limitation. The solver is hidden so that you cannot modify. These are everything are accessible by everyone. So you can go, you can modify anything, but be cautious and whenever you're modifying the source code itself, because it is very difficult. Once you modify it again, you cannot do it back to the original if you're not knowing it. So better, if you unknowingly did it also, try to uninstall the entire software, try to install. So better I suggest is spend time first to run some simulation. After that, once you become well expertise, you can touch the source codes, like modifying the code. For example, in our simulation, we're going showing an incompressible form, the ICO form. Okay, so this is the entire script. I don't know whether you have seen before any was CFD codes. Okay. Okay, I think whether this is visible to be on this size. Okay, I think this might be visible. Okay, this is this program to solve the incompressible flows. So you can go, these are the header files. So once you learn C++, you will find this is the comments. So this never include anything, but you see the description of solver. It is a transient solver for incompressible laminar flow of Newtonian fluid. So you need to be familiar with engineering terms. And this is the entire solver. So you see hardly how many lines are there. This much is the entire code. That's all. Okay, it has some dependency of using some other function. So this is how an code looks like for a CFD software. So basically what I showed you before, how to solve this momentum equation which it solves. Okay, so you spend time in knowing how the equation is built. You can write it back again with the mathematical equation and trying to find it out. Okay, so this is a solver. You can modify anything. There is no restriction on you. You can modify whatever you want. So but you need to be familiar with the thing. Okay, so now we'll try to see a demo. Okay, so how to use this tool, I'll tell you. So you want to solve some basic problems. So better first you need to go to the tutorials. Okay, first you need to go to the tutorials. You in this case, what I'm going to do is I'm going to solve an incompressible flow and icoform based. Okay, there are multiple things also which you try to spend every day trying opening one thing and trying to run it, and it's very simple. Okay, take this icoform. I'm going to run this elbow. Okay, so this is a problem which I'm going to run. So I'll try. What I need to do is, I should not do anything in the tutorial. What I'll first do is, generally I'll copy this file. Okay, I'll copy it and paste it in some other place, like where I want to modify it and do the changes. So in that way I've done it before itself. Okay, so I have copied and pasted it here. Okay, so this is the file which you will be using to solve the CFD problem. Okay, so how to, first I'll open and show you the files. I told you there are 3 folders basically. Okay, you leave all the rest of the part up, the rest. First we will see what is there inside this thing. There is a 0 file. Okay, there is something called P and U. This is the pressure values of the initial conditions of the pressure value. This is the initial condition of the velocity value. So what is this pressure values? I go again, I'll tell you, try to install this software also, Notepad++. This is again an open source tool and very effective for developers and this kind of text based softwares, which will be really helpful. So try using this Notepad++. Okay, so this is the software. Okay, this is a script of the pressure value. So what you observe from this, there is some header file which tells you it is an open field and manipulation, the OPENFOAM, where you got this tool developer and what version it is, what it is written in form, ASCII file, that is which an human can read. A binary file you cannot read, a computer can directly read. An ASCII file will be converted into binary file before execution. Then what class of file it is and what object it is going to read. It is going to read the pressure value, which is P, and dimension. You can see what it is. Next, these are the boundary condition. So these are like the boundaries at which the values exist. Okay, what does it state? Before getting to know about what is this value, I'll show you the geometry what we are trying to work. Okay, once you install OPENFOAM, you will find something called open like this logo with, okay, OPENFOAM. Try to double click it. First you will be getting this command line, then you wait for some minute, you will be getting the this line. Once you have got this line, then you are ready to start the thing. First, these are like some text based commands, so I don't want to spend time in teaching you the command lines of Linux, but I want to tell you how to progress through the simulation. So first what I'm doing is, first I'm changing my directory. That means first it is located at this location. My terminal is located at C drive, OPENFOAM, and the developer when it is located. So I have copied the file to some other location which is in E drive. So first I'll read CD and E. So now we can see it has changed to E. Okay, now CD means change directory. You should give CD space. I'm using presentation. Inside that KCG, inside that elbow. Okay, I give enter. Okay, so this is the directory which I'm going to, which has my file, which is already just a copy paste the tutorial and here. So I'm going to use one tool called parafoam. Okay, okay, before that I'll tell you one more thing. Okay, this has a mesh file from ANSYS Fluent. Okay, so it is a mesh file from ANSYS. Okay, that mesh I'm going to use it to solve this problem. So I want to convert this mesh. So in the before some slides I told you how to convert using some command. So in this one you can see how I'm going to convert that mesh. The file name is elbow.msh. So what I'm going to do is, I'm going to first write the command. See, there is 2 options which is available to you. Me mesh. Okay, so you can see I have written fluent mesh to foam.exe space. You need to give that particular file name elbow.msh and give enter. Once you give, you wait for some time. See. Okay, now what it has done is, this is basically, it converts those files into, this is a execution of that particular mesh file into OPENFOAM platform. So once you can see, it has written those mesh file into constant file. Inside that there is a folder which is created called polymesh. Again, you can go to the particular thing, constant, you can see something called polymesh. Inside that, this ANSYS mesh is split into this particular thing. This is how an OpenFOAM can understand the particular software, a particular way to solve it using OpenFOAM. So basically we need to understand it is being split into this one. I'm not going to tell you, we should always remember those things. It is not required at the initial phase at least. So I just converted that this particular file into the OpenFOAM readable one. Okay, so now what I'm going to do is I'm going to open this, the first GUI based thing which you're going to see, that is called parafoam. Parafoam. Okay, I'll open parafoam. Okay, what is this is again a GUI based, because you can generally set up the solver everything using text based, but outputs obviously we need some GUI based post processing tool. So one of the post processing tool which now we are trying to see is the parafoam. Okay, once you wait for some time. Okay, there is one more question in the meanwhile I'll answer. There is a question on whether it can solve only the flow analysis, or it can be used for structural also. It can be used for structural also, but it is not well matured as some other software. In open source, there is one more software called CodeAster, which you can try it learning those open source tool also. That is also free to access only. So I think you can use those things which are well matured in the field of structures, whereas you can solve some basic problems. There's no limitation, but if you're able to program yourself the structural problem, solve it, OpenFOAM can handle it. So you need to become little much matured in handling some equation which you need to convert it into C++ platform. Okay, next now we are going to see what is the file. Okay, I'm opening that particular thing, giving apply. Okay, so this is the file, this is the geometry which we are trying to analyze. Okay, so basically the mesh looks like this one. Okay, this is the mesh. One important thing is OpenFOAM always solves in 3D only. So whatever mesh you generate, it will be converted into 3D only. So you can see here, it is extruded in the third dimension. So OpenFOAM only solves in 3D. So even if it's a 2D, no problem. It will directly when you are converting the mesh, it converts into 3D. It will add one extra Z coordinates and solves it. Okay. So this is the geometry. Here you can see the mesh is not very great and all, so it is fundamentally a very basic mesh, which is I won't recommend this kinds of mesh in the initial, maybe in the initial phase. Okay, but later phase you need to spend a lot of time in doing a proper mesh, but this for learning purpose. Okay, this one is not very bad. So I'm going to use this mesh to solve the problem. Okay, it has two inlets, one from the bottom, one from the left side, two inlets, and flow gets mixed through this region and gets out through this one. Okay, so this is the problem which you are trying to solve. Again, getting back to the scripts, getting back to the script. So now I converted the mesh. There is a zero file which I showed you. What there are some scripts inside the P and U. So inside P you get these kinds of boundaries, which are this one's this curved, this has one boundary, this has one boundary, this and this, and these are the your inlets. Okay, so these are the typically these are the inputs which we have given. Okay, if it's a velocity inlet, for pressure it should be a zero gradient. So you need to get familiarized with some direct engineering terminologies, because I told you these are not developed by some one country people, because it is developed by multiple country people. So you need to be familiar with the mathematics and the mathematical representation of the engineering terminologies. Okay, so pressure outlet, what value you're going to have it at the outlet, 0 pascal. Okay, then the wall, what type of zero gradient, and front and back. Front and back is used for 3D case. That means like once you do a 2D simulation also, the this part is the front and this part is the back, the sectional view I'm telling. So what it tells you is like there is no flow across these things. It is just a symmetric plane. Okay, this is the pressure. Similarly, you can check the velocity also. It is built like that same way. Next I'm going to show on constant. Okay, constant as transport property. These are not going to be much important at the moment. Now this is the important part. So in this one you see there is some file called CONTROLDICT. You leave these two parts alone. Okay, these are the things I extra added to do the parallel simulation. This part is parallel simulation, this one is not required. So what is this CONTROLDICT is? So CONTROLDICT will have something like ICOFOAM. This is the script which we can modify anything. So I'm going to basically do the simulation. Consider for it starts from 0 second and I'm going to do it for 50-second simulation, because the transient solver, and how much time interval I need. It is going to do a simulation for delta t, that is a time interval for each simulation. I told you this governing equation is solved over this mesh. You need to know how much what is the time interval between each time step. So this gives you the time step, then the right interval, then the purge. And there's a question also, can we be able to do meshing in OpenFOAM? Yes, you can do it, Balaji. You can do it. There is some text files which I've added to the PPT. You can check it. And it requires some time for you to do it in OpenFOAM, but it is really easy only, not very difficult. Some basic geometry can do it, but if you want to do it complex geometry, then at least you should have learned how to do it in OpenFOAM, a basic simulation. So first you initially start with doing some basic simulation like how I'm doing. Later you can do the mesh. There is something called, if you want to do it for much very complicated geometry, there is something called snappyx. There's again a command line text which you need to tweak the mesh, tweak that script file to get your work done. Okay. Next, okay, in the CONTROLDICT you get what time you want to write, how much interval you want to write, what is should be the file output, how much precision you want to write the pressure values, pressure, velocity, or some other outputs also. Next, you want to modify the script in the runtime. These are things once you start doing it, you can do it. You can completely learn it and execute it. Okay. Next is FE schemes. Okay, this is again a script file. Now you can see what kind of schemes, because you see your governing equation is built with some differentials, some Laplacian transform, then some divergence, and then some gradients. So how you want to solve this one? Use Eulerian method. See, this is Gauss linear method and Gauss limited linear. So these are things which you need to get to know these things through documentation, like which schemes to, what are the other schemes available to you. You need to do it only by using it through some documentation. So some documentation which I have attached at the end of this presentation, which will be helpful for you to get to know what are the other schemes which you can use. So give a try using other schemes also. Okay, what are the interpolation scheme, what interpolation, linear or quadratic, or what scheme you want to use. Okay, next is FE solution. Okay, so what kind of how you're going to calculate the pressure based solvers or coupled or segregate solver. These are the things. Once you learn CFT, you will be getting to know what are these things and all. Okay, if you don't know certain terminologies, what is this solver, PCG and all, you can, what you can do is you go to the documentation, read it, what is this one, or go to this particular FE solution file documentation, you get to know all the other options also available. Okay, so once you get to know these are the files which are available to you, now I'll start the simulation. Okay, so what I'm going to do is, first I need to go to the command prompt. Okay, so I'm going to start. Okay, I've cleared everything. Now I'm going to start it fresh, the command prompt. So what I'm going to do is, I have before itself converted the mesh, so I'm just want to execute it. So this solver uses icofoam. Okay, the solver which I'm going to use is icofoam. Okay, if I go to this particular directory and enter icofoam, it is going to start solving it. Okay, I'm going to give enter, and you need to wait for it. Okay, so basically it is running a lot of things. Okay, okay, so see, it has completed the run. You can see since I have zoomed, it is not able to show all the things at the same time, but still it is running. At the end of the time, I'll tell you what is this numbers, and I'll like give a glimpse of what is these numbers. Okay, so see, it has run for 50 seconds. Okay, the simulation is completed for 50 seconds. These are some terminologies which are related to CFD, so you spend some time learning some CFD, learning the CFD. So you will be getting to know what are these particular pure number. These are very important terminologies, terms specifically to get a stable result, because numerical solution is a problem of instability. That means due to this round of error and truncation error and other improper setting of the condition, you may find the solver may diverge. Okay, so you need to get to know these terminologies. Then it is solving for P. Okay, using the schemes which you told it to do, and then it is finding some residual, what is the initial residual, final residual. Okay, now it has completed the simulation. Okay, now after completion, what we are trying to do is, we are going to again see the results. Before seeing the results, what we are going to do is, we are going to convert that particular file. Now you can see, okay, it is done. So what changes have happened to my file? See, now you can see from 0 time, now it has calculated the time output for 50 time. These are that 50 times. So what does this file inside these things will have? Go inside, it will have what is the pressure value throughout that entire field. What is the pressure value throughout that? What is the phi value throughout that entire field? What is the u value throughout that entire field for times 1 for 1 second? What is happening through what each second? So it has compiled and got the output for 50 seconds. Okay, next what you're going to do is, we are going to recompile all this thing back. So there is one more command line which you need to remember, this commands only. So it is called foam to BTK. Okay, if you give this one, what it does is, it compiles that particular files, everything. See, it is compiling that particular files together into a single file, so that you can access it. See, you can see that at time 24, it is compiling that particular files together. Same like that, it is doing it throughout. See, it has completed for 50 seconds. You can see it has completed for 50 seconds. It has recompiled. So again, you go to the folder and see, you find something called VTK folder. Inside this, you get your output for individual time. Now what you're going to do is you're going to see the output, how it looks. So the output will be like, you need to again open Paraform, which I told you that is a GUI based thing for. Okay, now again I'm opening the Paraform, which again I'm going to utilize to see the output. So whatever tool I showed you was completely free to access, the GUI based everything. Once you install the particular OpenFOAM installation using that particular installation guide, installation file, you will be included with these softwares only. Okay, so I'm going to open, go to VTK, and I'm going to open this one. I've opened this one. I'm going to apply. Okay, so what variable I'm interested in velocity. So if I give velocity, then here is option to play. So here you can see how the flow is developing. Okay, so in this way you can do the simulation for multiple kinds of geometry also. This is a very fundamental thing which I'm trying to teach you, is to get to know the tool. Don't be worried on how to start and all. It's very fun, very much easy. Just copy paste some examples from the tutorial. Inside that, go to the particular folder, go inside that, try to get it, copy it, and try to run it. Okay, so basically this was a small demo for you, so that you get to know what does this tool is all about. Okay, now, okay, so the OpenFOAM has once you install, you will be finding this kinds of folders which I showed you in my, like how you see it in my computer, how you see it. Next is, so this is an important page. Maybe as a beginner for you, you will be getting to know a lot of things through this page. Try to spend time opening all these links, because if you want to, because I gave you, I was here to motivate you to start learning open source tool, and I'm trying to utilize the OpenFOAM to do it. Okay, so in that way, I'm making you to start thinking about using OpenFOAM or open source tools to do your bachelor's project or your upcoming projects, rather than depending upon ANSYS or any other commercial software. So this one, these are some links from different organizations which they are provided as a resource material to learn OpenFOAM. Okay, so thank you for your attention, and I have something to tell as students, because the key point which I never was shown as a limelight when I was graduating. So I want to show you some key points where you can learn in your future all those things when you are like now the world panic level, there is a lot of unemployment, all are going to start. So how you can really work on some project without any investment or something. So there is one special website called GitHub. So okay, this is a one special website which you can spend time. Okay, what is this GitHub? I'll tell you. Okay, GitHub is something like a Google, you think. Okay, you may think, what is Google Chrome? Google Chrome belongs to Google, but actually it is not like that. Google Chrome doesn't belongs to Google, whereas you can show you. Okay, see, the Google Chrome was first developed by GitHub. See, again, GitHub is not any big organization or something. It's very big, but it's not like a organization which pays the developers some salary, nothing like that. This, whenever you are free, you can do a lot of projects in this. Okay, so what you need to do is you need to just sign up in GitHub. Okay, this is I'm not promoting GitHub or something. It is just a open source platform where all the people can work and contribute to get the softwares developed or anything. Okay, so you can see, like I'll show you OpenFOAM. There's a lot of introductory videos on GitHub and all. You can spend time. So how things work is, just first you need to know what kind of project you are going to work. Okay, for example, maybe you may be interested, okay, I don't want to use CATIA or SolidWorks, I want to use a free software which can do some basic CAD modeling. Okay, not very complicated, some 100 geometries assembling all together, not like that, but a basic geometry for your bachelor's project. So I see all the organization cannot afford you to give some license to do all those work. So what you will be doing is, generally you may be starting to work on some free tools. Okay, so I'll show you one free tool called FreeCAD. Okay, this is a open source CAD tool. Okay, so this is an open source CAD tool. Okay, this one, if you go inside this one, okay, see, this is the source code of the file, so you can download and see these are the some output of the CAD model which you can do it from this thing. So you can use this platform to do a lot of development. Okay, basically you need to sign up. Okay, then you can download this file, you can modify the script. Okay, for example, this one is developed upon, I think, C++. Okay, see, FreeCAD is developed on C++ platform. Okay, so you should be familiar with C++ to modify the code. See, it is updated 1 hour ago, and the updaters are not someone who get paid and all, but they do it at their free time to develop these things, and it's free access to everyone. So any student, any professor, anyone can access this tool to do their work, and it can handle some good decent amount of CAD models, not like a CAD model which can be done by SolidWorks, not to the higher level, but a decent amount, which would be more than sufficient for a bachelor students to be done, I guess. So like this way, you can do a lot of things. There are a lot of softwares in it. For example, if you want to develop for CFD, you can search for CFD. There are a lot of CFD developers. There are, see, in OpenFOAM, there are a lot of things are there. Okay, in open source regarding to CFD. So you can choose any. So for example, you want to choose some, these are a language which it has been used. If you want to use MATLAB to solve it, go to MATLAB. See, there is a person who has developed a convolution neural networking for fluid flows prediction of a bluff bodies. Okay, you can go to this particular tool, you can download it, you can modify the script. See, these are MATLAB scripts. Okay, so you can modify the scripts and you can run it. So what you can do is, for example, you are interested in this particular project. What you can do is, you can post this particular, you can download, you can clone or download this one, modify it, and you can upload it back in this one. So the developer, the owner of this particular project will see it. Okay, this option is added, so this is really helpful for a lot of our users, so I'll add it to the next version. So in the upcoming version, they will give it to you. They'll give it as a they'll give it in the common platform, they'll give it here again. for everyone to utilize that particular option. So the software gets developed like this only. Google Chrome also developed. Later what happened, it was not first initially released under the name called Chromium. Okay, it was not Google Chrome. First of all, it is Chromium. So Chromium, what they did was, Google took this open source, like how I'm doing, like I download this one, they make it as a Google Chrome. They got the source code from that GitHub only. They got it from this GitHub. This center platform where all the developers develop and put their code. Even you can contribute to that. Any developer, no one is going to question you why you are working on my code. And one more important thing is, they're not going to pay you at the initial phase, but you can learn things which you cannot do it until you get recruited by some MNCs. So you can spend a lot of time to download this one, modify it, the code, try to run it. You see some other features you try to add to that particular code, or you develop a new software itself, new CFD code fundamentally for anything. Then that code you upload it in here, so that some other developers will be interested to work on that, so that your software will go to the next stages. So it is very much easy. So it is basically, you need to spend a lot of time in doing it. Okay, so in this way you can build your platform well and good, so that you don't need to wait for someone to recruit you. At least until you get recruited, spend a lot of time in these kinds of platform. Okay, so that you get to familiar like what an industrial software look like, more than going to an organization and doing it. Those things were in the past. Many people do as a freelancing. How they do is, they sit on GitHub, they develop it, they upload the software. If the developer accepts it, that particular version comes into the, once it is accepted in the upcoming releases, your contribution, you can add to your portfolio, your resume is like, okay, I have done this thing, this particular development for this particular software, and it was accepted and released in the because the developer adds your name to the contributor list. So once you see, you will be getting to know what are the contribution you have done, and you can add it, so that even you have zero experience, you work like this parallelly without no one's help or support or anything. You can develop your own portfolio, and then you start uploading your trying to get benefited from this thing, upload these skills into your resume, and recruiters will be interested. Because the basic problem I see with the young engineers is, everyone asks for 1 year experience, 2 year experience. This is a very generic thing which happens, because all the company cannot recruit a fresher. Okay, so in this reason, I'm telling you, you spend some time when you're free, when you're like about to sleep, just to first you download the software, get to know that one particular program is very good. That only I'm telling. First spend at least 3 months in learning programming language, anyone in that particular platform, whatever your field of interest. Try to see what software is being available. Then you download that software. First you understand how they are built, not the entire software, and they don't have proper documentation for it. That is the only drawback. So you need to spend trial and error doing it. Once you have done it, what you do is, you try to develop it, then you try to submit to the developer. Okay, developer will see, okay, this particular feature from the any other software, you would have got inspiration from any others. For example, CATIA may have one option which a FreeCAD may not be having it. You try to program those things into a FreeCAD and giving to the contributor. He will accept it, means you get promoted. Okay, you tend to promote yourself to use those tools. Okay, once you get it, add it to your resume, stating like, okay, I've done this contribution to this one, and it was updated in the this version of the release. Then you increase your profile. Okay, so in this way, try to spend time. Okay, and you will be getting very good opportunity in future as you work on indirectly on these things, or you can work fully on freelancing, like developing a particular version of software, giving it in like this way, and you can do it. There is a lot of opportunity using GitHub. Okay, so try to explore this particular thing. You will find a lot of tutorials on how to use GitHub and all, because I have not touched in depth of anything. I'm making here you to motivate you to start using some other different thing, which it is not easy for you to get a visually initial phase, but later you may be realizing, okay, this is a better option, which you would have known in the past, means you would have helped you. So you are young, try to learn programming language, try to spend time. I'm not restricting you to any programming language. It is your wish of whichever interest but try learning one programming language, at least minimum two. Okay, and learn it at your level best, and try to explore these kinds of opportunity which are really worth and over a long run, not like for 1 or 2 years. I'm telling these things will be there for next to 50 to 60 or more than that. Okay. And I would like to thank everyone for being attentive to this session. I don't know how much it was helpful, but I'm here to motivate you to learn something which would be better for your future, which will really help you. Okay. Any questions or something you want to ask or any other thing, you can post it.
Dinesh, there was a question about particle methods
Particle methods.
by
Okay.
Balaji Parthivan.
Okay. Oh, like particle methods are like, for example, you cannot. There will be some problems like you want to find the solution for a discrete elements. Okay. There is two methods in CFD. Okay. One is continuous method, discrete method. So particle methods are a discrete method where you don't create this mesh. Rather, what you do, from inlet, you inject some particles with some initial condition. You observe how this particles value changes. Those are particle methods. So it is a discrete method, not a finite volume method. It's a discrete method. Okay, it is slightly different, and you need to know about particles natures, like particles collusion, then particles evaporation. It can evaporate, or particle can create, particle can generate, all those things included. Okay, so these things is a part of those studies. Okay, I hope he gets the answer.
There is another question by Parthivan, Balaji Parthivan.
Okay. Okay.
Sir, in OpenFOAM, we shouldn't give the final boundary conditions.
Actually, there is no final boundary condition or initial or anything. It is only one boundary condition, that is initial boundary condition, which is going to remain constant throughout the problem. Okay, so once you give some boundary condition initially, for example, a pipe is there or anything, you are trying to give the boundary condition at the wall. Okay, it is not going to have any velocity to the wall. So this boundary condition remains constant throughout the problem. So it is not going to change. So the boundary condition till the final, from the initial to final, is going to be the same. So you don't need to specify any final boundary condition. All are going to be the same boundary condition.
I think we are done with the questions. There was one question by Mohan for suggestion for structural analysis. I think we can take it offline. Any other questions from panelists? Okay, we have one from Balaji again.
Okay.
And Sanjeevi.
Okay. In case of common vortex flow, you are asking. Okay. In common vortex flow, the boundary condition remains still only the Reynolds number of the flow only matters. Okay. So it's unsteady, and if your Reynolds number is below some 100, you will be able to get your results. Okay, it is basically doesn't deals with any boundary condition. Only the property is a cylinder with immersed in a Reynolds in a flow with a Reynolds number of 100 will be experiencing it. Okay.
I think we are done with the questions. If any other questions are there, I'll share the mail ID of Mr. Dinesh to your mail IDs. Right? So for the participants who have attended, you can ask any questions. He will be ready to help. Thank you, Dinesh. I request Shyam Narayanan to make a closure.
Thank you, Professor Venkatramanan. So on the behalf of the Department of Aeronautical Engineering and KCG College of Technology, I would like to share my sincere gratitude to Mr. Dinesh for the valuable and informative webinar on Introduction to OpenFOAM. Thank you, our HOD, Professor Vijayaraja, Alumni Coordinator, Mr. Venkatramanan, and KCG Alumni Connect team for arranging this webinar. Thank you to our principal, Dr. G. Prabhakaran, Associate Dean, Professor Devasundari Ma'am, HOD Electronics Department, HOD Mechanical Department, and management for the support and providing this online platform. Thank you all of our participants for your valuable suggestion, and thank you for our panel members. Special thanks to our Singh sir, HOD Chandigarh University Aerospace Department. Once again, I would like to thank Mr. Dinesh. I am expecting your help and support for our students and your juniors in your future events. And thank you, Mr. Nibin, for the technical assistance and support. Thank you, Mr. Dinesh.
Thank you.
Okay, thank you. If there is no other comments by any of the panelists, I would request you to give some comments from your side. Please, sir.
Dinesh, thank you very much for your nice presentation. I think it may be very useful for our students. They may place the OpenFOAM during the lockdown period. They can learn something what you teach today. I hope all of you enjoyed that one. Very nice presentation. Thank you, Dinesh.
Thank you. Anyone else?
Yeah, thank you, Dinesh. This is Asad here.
Yes, sir. Yes.
Yeah, it was a very nice presentation. Yeah, it was more like a workshop than a webinar. So I think the experience would have helped, and I think students would have immensely benefited. I think I hope all the best for you in your career and your aspirations as well. And I think best all has been added. So thank you very much.